Okay, now we will discuss about the method of solving second order linear homogeneous differential equation. Solving second order linear homogeneous differential equation. So so there are various methods, and there is a technique that is use of a known solution to find another. So for second order linear differential equation, we saw that y1 and y2 are two linearly independent solutions. Any two linearly independent solutions, then if we know one solution y1, then we can find out y2. There is a technique that is the use of known solution to find another. So suppose that is the technique is use of known solution. So if y1 is known, suppose y1 is known, then y2 can be calculated from this formula. Y2 equal to y1 integration e to the power minus integration p of p dx by y1 square into dx. We will not discuss about it in detail. Just uh, you have to remember this for formula. If y1 is known, then how to find out the another solution y2. So you have to apply this formula. So here p is the that is the coefficient of that here p e to the minus pdx is the integrating factor, and here p is the coefficient of the dy dx, that is the first derivative of y. Now we will discuss about the homogeneous differential equation with constant coefficients. That is homogeneous differential equation with constant coefficient. So homogeneous differential equation with constant coefficient means the coefficient of y and dy dx and d2y dx2 is constant. So we can write the general expression of a homogeneous differential equation with constant coefficients in this way, that y double dash plus q, this is a constant coefficient of y dash plus q into y equal to 0. It is homogeneous, so that is why the right hand side term is equal to 0. So to solve this differential equation, and we have to start from a trial solution or a trial function. Now the starting point is the fact that that the trial solution should be in the form of a exponential function. Suppose there is e to the power x, because 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 the derivative of this function is itself the function, because the what I said, that the derivative of e to the power x is equal to e to the power x, which is the function itself. So if the function is suppose in this way, that e to the power mx, then the derivative of that function is written as a constant multiple of that function e to the power mx in this order. So for first order we write m into that function, and for second order we can write that is m square into that function. So this is the starting point. So so for this for solving this differential equation, uh, we have to start from this type of trial function or trial solution of this differential equation, and that means that is in this form, that is using this form we have to calculate the final form of the solution of this homogeneous differential equation having constant coefficients. So so let us consider if y equal to e to the power mx be the possible solution of that solutions of this differential equation. Then from this we can calculate y dash equal to m into e to the power mx, and y double dash equal to m square into e to the power mx. So now uh, so putting the value of y into that equation, homogeneous differential equation, that which is y double dash plus p into y dash plus q into y equal to 0. If so y double dash is m square e to the power mx plus p into m e to the power mx plus q into e to the power mx is equal to 0. So or that is m square plus pm plus q into e to the power mx is equal to 0. So in this condition either this term is equal to 0 or e to the power mx equal to 0. If this is the solution, then e to the power mx cannot be equal to 0, is not equal to 0. So we can write that m square plus pm plus q equal to 0. So from this we can calculate m, which is equal to, so m equal to minus p plus minus p square root over p square p square minus 4q by 2, because this equation has two roots, so it will have two values of m, that is suppose m1 is equal to minus p plus root over p square minus 4q by 2, and m2 is minus p minus root over p square minus 4q by 2. So we will discuss different cases for different types of this m. So we can write m1 and m2. So m1 is minus p plus root over p square minus 4q by 2, and m2 is minus p minus root over p square minus 4q by 2. So so the first case, suppose the m1 and m2 are real and distinct. Suppose the first case is m1 and m2 are real and real real and distinct. So m1 and m2 are different but real numbers. So when it is possible, when p square minus 4q is greater than 0, that means p square is greater than 4q. So so that m1 and m2 are real, and if they are distinct, so we can write the general solution of that differential equation, homogeneous differential equation, is y equal to that is the first solution, y1 equal to e to the power m1x, and y2 equal to e to the power m2x. These two solutions. So if m1 and m2 are real and distinct, then the two independent solutions are y1 equal to e to the power m1x and y2 equal to e to the power m1 m2x. They are independent, linearly independent, because the ratio of y1 y2 is not a function of x. This is not equal to constant. The ratio of y1 and 2 is not a constant. That is why we can say that y1 and y2 are linearly independent. So the general solution of this differential equation in this case, we can write y equal to c1 e to the power m1x plus c2 e to the power m2x. Now the second case is if m1 and m2 are complex and distinct. Suppose m1 and m2 are complex numbers, complex and distinct. If m1 and m2 are complex and distinct, then we can we can write m1 and m2 in the form. Suppose m1 and m2 is equal to a plus minus ib. So m1 and m2 complex when p square minus 4q is less than 0. That means p square less than 4q. So the m1 and m2 are complex. So the two solutions are independent solutions are y1 equal to the power m1x. That means e to the power ax in e to the power a plus ib into x, and y2 is equal to the power m2x. That means e to the power a minus ib into x. So the general solution is y equal to c1 e to the power a plus ib into x plus c2 e to the power a minus ib into x. And so this is the solution, and we can write that e to the power, taking the common, then this is c1 into this is e to the power ibx. That means cos bx plus I sine bx. This is the c1 and plus e to the power 0x. This is x, and so we can write c2 cos of bx. This is c2 cos of bx, and minus c2 sine of bx. I sine of bx. Now, so we can write e to the power x. This is equal to cos of b, c1 plus c2, and plus we can write sine of bx. That is I c1 minus IC2. So we can write y equal to e to the power ax. This is we can write it as, suppose that is c1 c1 dash cos of bx plus c2 dash sine of bx. So this is the solution. So here c1 dash is c1 plus c2 and c2 dash is equal to ic1 minus ic2. So this is a constant, so we can write c2 dash is this. So we can write also in this form e to the power ax. C1 c2 are all constant, so you can write c1 cos bx plus c2 sin bx. So this is the solution when m1 and m2 are complex and distinct. Now the third case is when m1 and m2 are equal and real. So m1 and m2 are real and equal. So real and equal, that means you can say m1 equal to m2. Suppose m suppose m, then the first solution y1 equal to e to the power m1x, that is e to the power mx. So the next solution, that is y2 equal to y1 integration e to the power minus integration p dx by y1 square into dx. So here y1 is e to the power mx, so e to the power mx integration e to the power minus p dx by y1 square, that means 1 square e to the power mx by 2, with mx by 2. Mx by 2 into dx. So now it will mx, and now here because it is a constant coefficient, so p must be constant, so we can write e to the power minus px by e to the power mx by 2 into dx. Now since the a1 and 2 are real and equal, so here that means p square minus 4q equal to 0. So p square minus 4q equal to 0, and so we can write am equal to p by 2 from that formula. So this formula, so this is equal to 0, that means m1 and m2 are minus p by 2, so it is minus p by 2. So it is m equal to minus p by 2. So this is equal to, so so we can write y2 equal to e to the power mx e to the power minus px by e to the power m, that means minus p by 2 by 2. Oh sorry, this is y1 square. This should be 2mx. This is 2mx 2mx. So 2mx dx is e to the power mx integration e to the power minus p of x by, here m is equal to minus p by 2, that means e to the power minus px into dx, that is x into e to the power mx. So if the roots are real and equal, then the solution y1 is e to the mx, and the next solution y2 is x into e to the power mx. So we can write the general solution as y equal to c1 e to the power mx plus c2 into x e to the power mx. So we can write e to the power mx into c1 plus c2x, which is the general solution of a homogeneous differential equation with constant coefficient uh, when the two roots are equal of this of this of this equation. So let us now discuss some examples. Suppose y double dash minus y equal to 0, and if y, so we have to solve this differential equation, homogeneous differential equation, and suppose y equal to e to the power mx is a trial solution, then we can get the auxiliary equation, which is m square minus 1 equal to 0. That means m minus 1 into m plus 1 equal to 0. So from this we get two values of m, which is m equal to plus 1 and minus 1. So the solution of this differential equation, that is the general solution, is y equal to c1 e to the power x plus c2 e to the power minus x. This is the solution. Now similarly, suppose the example 2, suppose the differential equation is this y double dash plus y equal to 0, and if y equal to e to the power mx is the trial solution, then the other equation we get is m square plus 1 equal to 0. So from this, m1 and m2 is equal to uh, I and minus I. So the general solution is y equal to e to the power e to the power, here the real part is 0, so this is equal to 0. So we can write c1 cos x plus c2 sine of x. Now if let us discuss the third example. If the differential equation is y double dash minus 2y plus 1 equal to 0, if y equal to e to the power mx is the trial solution, then we can write this is m square minus 2m plus 1 equal square equal to 0. So from this we can write m minus 1 equal to 0. So the value sum m is equal to m1 and m2 equal to 1. So the roots are equal and real. So the general solution of this differential equation, we can write y equal to e to the power here the value of m is 1 with e to the power x plus c1 plus c2 into x. This is the solution. Okay, next we will discuss about uh, second order non-homogeneous linear differential equations with constant coefficient. So we will discuss about the method of solving of second order non-homogeneous differential equation with constant coefficient. The solving second order non-homogeneous differential equation with constant coefficients. So second order non-homogeneous differential equation with constant coefficient can be written as in this way, that y double dash plus p of y dash plus q of y equal to r of x. So this is the non-homogeneous differential equation with constant coefficient. Now there are various methods of solving this non-homogeneous differential equation. Before discussing several methods, uh, mm, we write the complete solution of this non-homogeneous differential equation as that is y of x is equal to yg plus yp. So yg of x and this is of x. So here yg is the general solution of the homogeneous differential equation associated with this non-homogeneous differential equation, and yp is the particular solution of this non-homogeneous differential equation. So we will discuss two methods of solving the particular solution of this non-homogeneous differential equation. We know how to calculate the yg, that is the general solution of the homogeneous differential equation with constant coefficient, and then we have to find out yp, and then we have to do the sum of yg and yp to get the complete solution of a non-homogeneous differential equation with constant coefficients. So there are various methods. So the methods are the method of undetermined coefficients and operator method and variation of parameters. So we will discuss the variation of parameters method and operator method of solving the non-homogeneous differential equation, or to find out the particular solution of a non-homogeneous differential equation. So the method one we will discuss is the variation of parameters. Okay, variation of parameters method of calculating the particular solution of a non-homogeneous differential equation. So we have to find out the particular solution. So the formula is yp is equal to y1 integration minus y2 into rx by w into dx plus y2 into y1 r of x by w into dx. So we will discuss the method in detail. So this is the formula of calculating the particular solution yp of the non-homogeneous differential equation. So here w is the Wronskian, so w is equal to y1 y2 y1 dash y2 dash. So first we have to calculate w, then we have to find out yp, and then the complete solution is simply y equal to yg plus yp. So that is yg, that means c1 y1 plus c2 y2 plus yp. So this is the formula of solving a non-homogeneous differential equation using the variation of parameters. And so here this solution, there is the general solution of the, so this term is called the complementary function. It is sometimes it is called a complementary function, and this is called particular integral. Suppose the differential equation, suppose we have to solve this differential equation y double dash plus y equal to cosec of x. So the solution is, the complete solution of this differential equation is y of s is equal to c1 y1 plus c2 y2, which is the complementary function, plus yp of x. So we have to find out y1, y2 and yp, and then take the sum. So we have to add these three functions. So to calculate c1 y1 plus c2 y2, that is the complementary function, that is the solution of the homogeneous differential equation of this non-homogeneous differential equation. To write y double dash plus y equal to 0. So we have to obtain the homogeneous differential equation of this differential equation. Now suppose let us consider y equal to e to the power mx is the trial solution, and putting this into the differential equation, this homogeneous differential equation, we get that m square e to the power mx plus e to the power mx, this is equal to 0. So here m square plus 1 into e to the power mx equal to 0. Now e to the power mx cannot be equal to 0, so only this m square plus 1 is equal to 0. So we get m equal to m1. So the two values of m, there is a m1 and m2 is equal to I and minus I. So the general solution of this differential, this homogeneous differential equation is c1 cos x plus c2 sin x, where y1 equal to cos x and y2 equal to sin x. These are two independent solutions of this homogeneous differential equation. Now we have to calculate yp. So yp is equal to y1 integration minus y2 into r of x by w into dx plus y2 into y1 r of x by w into dx. So here the w, there is a Wronskian, is equal to y1, that is cos of x sin of x, then cos x integration, that is minus sin of x, and sin of integration derivative cos of x. So this is cos x squared x, plus sine square x, that is equal to 1. So w is not equal to 0 when which is 1. So we can write that y1 is cos x and y equal to minus sin x minus sin x, and r is cosec x into cosec of x by 1 into dx plus y2 which is sin x into r of x. Y1 is the cos x into cosec of x into dx. So yp is equal to minus x cos x plus sin x integration is cos x by sin x into dx, that is we can write minus x cos x plus sine of x is log of sine of x. So we get the particular solution. So the complete solution of this differential equation is y equal to c1 cos x plus c2 sin x minus x log x plus sine of x into log of sine x. So this is the complete solution. This is the complementary function, and this is the particular integral. Okay, now we will discuss about the operator method, and we will solve this differential equation, uh, this using the operator method, and we'll check whether the answers are same or not. So now we will discuss the operator method of solving the particular solution of a non-homogeneous differential equation. So we can write the nth order non-homogeneous differential equation with constant coefficients as dxn plus a1 d of n minus 1 dx. This is the nth derivative of y. This is the n minus 1th derivative of y plus up to a n minus 1 dy dx plus a n to y equal to f of x. So this is the general expression of a nth order differential equation with constant coefficient. Now let us represent the derivative by powers of d. So that is, the d is represented by the derivative, and the order of the derivative is represented by the power of the d. So if it is d square, then we can write d2 dx2. So if dy is written as dy dx, then d2y, this means d2y dx2. So this general expression can be written as dn plus a1 dn minus 1 plus dot dot plus a n minus 1, that is d plus say n, this is of y equal to f of x. Now this this can be represented as a function of d of y is equal to f of x. So this is the nth order or any order general expression of a non-homogeneous differential equation with constant coefficient in operator form, where fd is the function of the operator d, where d is the ddx. So this fd is can be written as polynomial function of the operator d. So this if this function can be factored into many parts, so in many roots, so this fd can be factored into many parts, so we can write since it is a polynomial function, then we can write into many parts, so d minus 1 into d of r2 to d minus rn, where this r1 r2 and rn is the roots of the auxiliary equation, which is f of d is equal to 0. This for this auxiliary equation, this r1 r2 rn, these are the roots of this equation. So for second order differential equation, it will have only the two roots, so that means it will have d minus r1 into d minus r2 into y equal to f of x. So we can obtain from this expression also for second order derivative, second order derivative, then this n equal to 2. So n equal to 2, that means it will have d2y plus, and this is a1 dy plus and this is a2 into y equal to f of x. So for second order, we can write this d2y plus a1 d of y plus a2 of y equal to f of x. So so that means we can write that is d square plus a1 into d plus a2 into y equal to f of x. So this can be factored into two parts because it will have two roots. So that which is written as d minus 1 into d minus r1 into d minus r2 into y equal to f of x. Now so the method of solving is is simply the integration actually. So the general expression of this differential equation, non-homogeneous differential equation, is this: f d of y equal to f of x. So so for first order, we write that is d of y equal to f of x. Suppose simple first order differential equation, which is dy dx equal to f of x. This is a first order differential equation, linear differential equation. So in the operator form, we can write in this way: d of y equal to f of x. So the solution is simply y equal to so here the solution y is equal to integration f of x dx. Then from this equation, we can write y equal to 1 by d f of x. So you see that the operator 1 by d is represented by the integral. So this is equivalent. So we can write 1b f of x, that means integration f of x dx. So this is the method of solving the differential equation. Now let us consider the first order linear differential equation, that is dy dx minus ry into equal to f of x. So this is the first order linear differential equation where r is a constant. Now so in the operator format we can write, that is d of minus of r into y equal to f of x. So from this we can write y equal to 1 by d minus r into f of x. So now if r equal to 0, so if r equal to 0, then we can simply get y equal to 1 by d f of x. So from this equation we know that the integrating factor is e to the power minus r dx. Since r is constant, then we can write e to the power minus rx. So multiplying both sides by e to the minus rx, then simply the solution of this differential equation is y equal to e to the power rx into e to the power minus rx into f of x dx. This is a simple calculation. We are not writing all the steps. So just if you multiply this equation, both sides of this equation by this integrating factor e to the minus rx, and the left hand side is simply dtx of y into e to the minus rx, and the right hand side is equal to e to the power minus rx into f of x. So y equal to e to the power rx integration e to the power minus rx into f of x dx. So so comparing these two equations, then we can write that 1 by d minus r f of x is equal to e to the power rx integration e to the power minus rx into fx dx. And if 1 by d f of x, then we can write this is simple f of x d of x, because when r equal to 0, then e to the power x and to the minus rx is 1. So so this is the this is the expression. This formula is needed for calculating the yp of a non-homogeneous differential equation.